This problem is from the textbook Conceptual Dynamics. This is example 2.2-2. The problem statement reads, a particle travels along a straight line with a velocity given by v equals 3 plus 12 times t minus 3 times t squared meters per second. When t equals 1 second, the particle is located 50 meters to the left of the origin. Determine the acceleration when t equals 4 seconds, the displacement from t equals 0 to t equals 10 seconds, and the total distance the particle travels during this time period. So looking at this problem, this is one of the sort of simpler problems that we're going to start with in this course. A couple things to note. This problem is regarding a particle, or we're modeling something as a particle. And so particles have mass but no size. We can consider them a point. And because of that, we basically are not interested in their rotation. We're only interested in their translation. So a particle is a simpler model than a rigid body model, and that's why we're starting with it. The other thing to note is that we're moving along a straight line. So we're just moving back and forth along a line. And so we're moving in one dimension, and this is called rectilinear motion. And again, this is the simplest sort of type of motion we can have. Finally, when I talked about particles, I mentioned that they had mass but no size. But in this problem, we're not going to consider the mass, and we're not going to consider any forces. This is what's called a kinematics problem. We're looking at the geometric and time aspects of the motion of the particle without regard to what's causing the motion. So in essence, we're just given information about its velocity. When we solve any problem in this course, we're going to follow a similar sort of procedure. And so the first thing that we want to do is we want to write down what's given in the problem. And so what we're given, one of the things we're given is the velocity of the particle as a function of time. The other thing that we're given is we're given the position of the particle when t equals 1 second. Okay. So what we should do is we should write that down. Looking at this expression for velocity, since we're moving along a straight line, since this is rectilinear motion, when the velocity is positive, in essence, that means we're moving to the right. And when the velocity is negative, that means we're moving to the left. So you can sort of imagine this particle moving along a number line where the numbers or the position gets larger to the right and it gets smaller, becoming negative as we move to the left. If we look at this, we're told that the units of the velocity are meters per second. Here we have these different coefficients, 3, 12, and negative 3, and they're multiplying different things, time squared, time, and then nothing. And so implicitly, these coefficients have units. So in order for the units of the total sum to come out to be meters per second, that means, for example, that the 3 must have units of meters per second. And for example, the 12 must have units of meters per second squared. In this case, we're sort of going to sort of leave that behind the scenes, but keep it in the back of your mind that all of these coefficients do have units. In future problems, these coefficients may have physical meaning. You know, they could be a stiffness, they could be a damping, they could be a mass, etc. And so the coefficients will have physical meaning. In this case, they don't as much. It's just the particle is moving in this way. And the units of the coefficients are just such that it makes the units of the velocity come out correctly. The other thing that we're given is this. In essence, you know, we're giving an initial condition or a boundary condition. We're told what the position of the particle is at t equals 1 second. And so we represent position here by the variable s. And again, you know, in general, position and velocity are vectors. so they have magnitude and direction. But in this problem, since it's rectilinear motion, we're going to capture the sort of direction just by sign. So the velocity is positive, we're moving to the right. When the velocity is negative, we're moving to the left. And similarly, the fact that we're to the left of the origin, our origin is sort of the zero of our number line. And so if we're to the left of zero, that means that we have moved into the negative direction or a negative position. When we move to the right, we move into a positive position. So the fact that we're to the left of origin means that we have a negative initial position, or not even necessarily an initial position, but our position at time equals 1 second. So that's usually the first step. Read the problem very thoroughly, try to understand it, write down what's given. The other thing that we like to write down is what we're going to find. And so I'll do that in a minute, but if we look at this, it basically seems that we want to find three different things. We want to first determine the acceleration when t equals 4 seconds. Next, we want to determine the displacement between t equals 0 and t equals 10 seconds. And then finally, we want to find the total distance the particle travels during this time period. So we'll basically do this example in 3 parts. Before we do that, though, something that's often helpful when we're trying to understand a problem is to draw a picture. So that's what we're going to do. We're going to go ahead and graph this velocity function to try and better understand what's going on. So here, again, we have this particle and it's moving along a line. This is our given information. So at t equals 1 second, our particle will be at minus 50. We actually don't know where it is at time equals 0 seconds. If we graph this function of velocity, we can graph it versus time. We can see that it's a quadratic, so it's going to be a parabola. The coefficient on the t squared term is negative, so it's going to be basically an upside down parabola. And so if we graph that maybe with your calculator, we can get a better sense of what's happening. So initially, we have some positive velocity, and the velocity initially gets bigger. So the particle is moving faster in the positive direction. So it's moving faster to the right. And then eventually it starts to slow down. So it's still positive, so it's still moving to the right, but it's moving to the right more slowly. Eventually, the velocity passes through 0 meters per second. And so at that point, the velocity becomes negative. And a negative velocity means that, in essence, we're moving backwards. We're moving in the negative direction, which is to the left. Okay? And so sometimes it can be a little hard to sort of take this graph, which is a function of time, and sort of translate it in your mind into what the particle is physically doing in space. But we're going to try and do that here with this little animation. It's not very accurate in the sense that it doesn't really capture the speed of the particle, but it will capture sort of the direction of motion. So initially, when the velocity is positive, the particle is moving to the right, and then at some time here, nearby 4 seconds, the velocity becomes negative, and so that means that the particle begins moving to the left. And so you can sort of imagine the particle doing something like that, moving to the right and then moving to the left. We don't really know where it is at time equals 0, and we don't really know where it is at time equals 10, but we know where it is at time equals 1 second, and we know what its velocity is across that whole time. So back to the problem statement, the first thing that we wanted to find was the acceleration at time equals 4 seconds. So this is what we're given. The velocity is a function of time, where this is the function, the position at time equals 1 second, and then we want to find the acceleration at 4 seconds. In general, we're sort of going to try to come up with a solution or a process that matches or connects what we're given to what we want to find. In these rectilinear kinematics problems, we can basically solve everything from these three equations. So velocity is the time derivative of position, acceleration is the time derivative of velocity, and then if we combine these two equations by eliminating the dt, we can come up with this other form of an equation. And so looking at what we're given velocity as a function of time, and we want to find acceleration. So looking at these equations, we also are given position at one time instant. So looking at this, which of these three equations connects everything that we want and are given? So we're given velocity as a function of time, and we want to find acceleration. So the only equation that has all three of those sort of variables, velocity, acceleration, and time, is this middle one. Okay, and so we can see, in essence, from this, if we take velocity and take the derivative with respect to time, we get acceleration. So acceleration is a derivative with respect to time, where velocity as a function of time is this, 3 plus 12t minus 3t squared. Remembering the rules for differentiation, the derivative of a constant is just 0. The derivative of 12t is t, the derivative of 12t is 12, the derivative with respect to time. And the derivative of minus 3t squared, when we have a polynomial like this, we bring down the exponent. So we have minus 3 multiplying 2, which gives us minus 6, and then we subtract 1 off the exponent. So 2 minus 1 is just 1. And so that gives us our expression for acceleration. Since we're dealing with units of length in meters and units of time in seconds, the units for acceleration are going to be meters per second squared. If we wanted to be sort of more precise, we could sort of go back to what the implied units of these coefficients are. So in order to make the velocity have units of meters per second, this 12 had to have units of meters per second squared. So that matches. And in order to, again, make this quantity have units of meters per second, the 3 would have to have units of meters per second cubed, so that the seconds cubed canceled with the seconds squared there, leaving just a seconds in the denominator. And so if this has units of meters per second cubed times seconds, again, we get meters per second squared as we desired. So that is the expression for acceleration over all time. We specifically want to know the acceleration at time equals 4 seconds. So all we do is simply substitute 4 in for time. So 12 minus 6 times 4, 12 minus 24 is negative 12 meters per second squared. So that is the acceleration at time equals 4 seconds. That was what was the first thing that was asked for in the problem. The second thing that was asked for in the problem was the displacement between time equals 0 seconds and time equals 10 seconds. And so this displacement, or this change in position, will represent with the delta. And specifically what we're interested in is the difference between our final position and our initial position, the displacement between 0 seconds and 10 seconds. Again, we want to sort of connect what is given in the problem to what it is we're attempting to find. So we have velocity as a function of time, we have a position at a given time, and we're trying to find the change in position, or the displacement. We also implicitly have an expression for acceleration from the previous part of the problem. So again, looking at these sort of three basic equations that we're going to be using, looking to connect v, time, and s. The equation that does that is this one. In particular, we're trying to solve for s. So if we solve, we can in essence solve this for s. So looking at this dt and this ds, these are differential elements. So they're just, we can think of them as small increments of time, small changes in time or small changes in position. And so they're just numbers. They can be multiplied or divided just like any variable. And so if I do that, if I multiply through by dt, I can in essence solve for ds. So I just multiply the dt to the other side. And so I'm getting closer to isolating s, isolating the thing we're trying to solve for. In essence, right now I have an expression for a differential. I don't want a differential element of position or change in position. I want the whole expression for position or the whole displacement. And so in essence, I need to add up all of the differential elements. To get the total change in position, I need to add up all of the small differential changes in position. And the way that we do that summation is with an integral. And so you can sort of think of this integral symbol as an S representing a summation. This integral we can solve because we have velocity as a function of time. Since we have velocity as a function of time, we are able to integrate with respect to time. So I can go ahead and substitute that expression for velocity. This is sort of the most common sort of situation where we're given things as functions of time, but that's not always the case. And so we have to be careful when we do our integration or when we do our differentiation that we know what we're integrating with respect to and what we're differentiating with respect to. You know, there are many instances where things are functions of something other than time. For example, acceleration due to drag, that acceleration tends to be a function of velocity. And so if we had something as a function of velocity, we could not integrate it with respect to time. We would want to integrate it with respect to velocity. And so there are other examples in the book that capture that case. Okay, so looking at this, we have an integral. Right now, it's an indefinite integral. We have no limits on the integrals. If we were to integrate this integral, we would end up with a constant of integration, a plus c. If we add boundaries, if we add limits to our integral, then we can evaluate the integral at those limits. And so what we're going to do here, in essence, we want the displacement between 0 and 10. So we could attempt to integrate between 0 seconds and 10 seconds. The only problem is we don't know the position at 0 or 10. So what I'm going to go ahead and do is I'm going to use 1 second as one of my limits because we do have the value of the position at 1 second. So I'm going to integrate from time equals 1 second, where s is equal to minus 50. And then I'm going to go ahead and leave the upper limit as a variable. So it's just some variable s, some variable t. Even if we had been given the boundaries of 0 and 10, you know, for example, I could put 0 here and 10 here, or 1 here and 10 here, and then solve for the position at 10. It is often better to solve things symbolically. It is often better to leave this upper limit as a variable s as opposed to a specific time or a specific position, because that symbolic expression that we're going to end up with could be useful in other ways. It could be useful for another part of the problem. for example, what we're going to do in part C. It could also be useful for sort of a sanity check. It gives us something to sort of plug in some numbers into to sort of check or to graph to see if this makes sense. So keeping that in mind, we'll go ahead and evaluate this integral. This integral, we can sort of imagine that there's a 1 here. So the antiderivative of 1 is just going to be s. Evaluate it between the limits minus 50 and s. On the right-hand side, we'll evaluate that integral. The antiderivative of 3 is 3t. The antiderivative of 12t. We add 1 to the exponent, and then we divide the 12 by the new exponent, which is 2, 6t. And so you can see if we differentiated this, we would get back our 12t. And then here, for the last term, we add 1 to the exponent, so it becomes t cubed. We divide the coefficient by 3, get minus 1. And that is our solution, and this is positive. And so when we solve that integral, we basically split it across the addition and the subtraction, which we're able to do. That is a property of integrals, that you can split them over integration, or you can split them over sums and differences. And that makes sense because an integral is just a sum. So, and then we evaluate that between the limits 1 and t. Then we plug in our limits. So we get s minus negative 50. On the right-hand side, we plug in t. Just gives us the same expression, 3t plus 6t squared minus t cubed. And then we subtract the expression evaluated at 1. So 3 times 1 plus 6 times 1 squared minus 1 cubed. And then if we solve for s, so over here we have this expression, 3 plus 6 minus 1, so that's 9, minus 1 is 8, negative 8. And then here we have a positive 50 when we subtract it to the other side. We have negative 8 minus 50 is minus 58. And plus 3t plus 6t squared minus t cubed. So that's our expression for position. And it's a symbolic expression. It's a position as a function of time. Once we have that, we can then go ahead and solve the displacement. So in particular, we want the displacement between 10 seconds and 0 seconds. If we take time equals t and plug in 10 for t here, we get minus 428 meters. So again, this has units of meters because that's the units of length we're dealing with. If we wanted to do all the bookkeeping for the coefficients of 3, 12, and negative 3, the units would work out correctly when you did the multiplication. Then we want the position at time equals 0, so we plug in 0 for time, get negative 58 meters. So minus 428, subtracting a negative number is like addition, so it's adding 58. It works out to be minus 370 meters. Okay. And that's the solution to the second part of the problem. Since the displacement is negative, that means that the particle ended up further to the left than it started from. So it ended up 370 meters to the left from where it began. And the final thing that we're asked for is the total distance traveled. And I'll express that by this variable. And so total distance traveled is different than displacement. So displacement has no regard for sort of how we're moving. It's just the difference between where the particle started and where it ended. It doesn't care what it did in between those two time instances. Displacement doesn't rely on what it did between 0 seconds and 10 seconds. Total distance traveled, however, does. If we remember back to what our particle did, we know that the velocity started off positive, so we moved to the right, and then it became negative, and we moved to the left. And so in this case, the total distance traveled will be how far we moved forward plus how far we moved backwards. Total distance traveled is a scalar. It's not a vector. It doesn't care the direction of motion, whether we move to the right or to the left. We just want to know the total distance traveled. From part B, this isn't necessary exactly, but from part B, we knew that we started at minus 58 at time equals 0, that's where we are. And then time equals 1, we know that we're at 50 seconds. At some point, we turn around, and then we know that we end up at minus 428 meters at t equals 10 seconds. Therefore, in order to determine the total distance traveled, we need to figure out where we turned around. How far did we go forward? How far did we go to the right before we went backwards? And so in order to figure that out, we need to determine the time at which we turned around. So when does the particle turn? And so the particle turns when the velocity changes sign. When the velocity is positive, we're moving to the right. And then when the velocity is negative, we're moving to the left. This was a quadratic. If we recall, it was positive and then it was negative. So going back to this previous slide, we were positive and then we were negative. And so this point at which the velocity changed sign is where we had our turn. So in essence, we want to find when velocity is equal to 0. And that's basically just the solution of a quadratic equation. So when v equals 0, or more specifically, when v changes sign. So we want to know, when does this equal 0? We can use the quadratic formula. The roots of this equation, it's minus b plus or minus the square root b squared minus 4ac divided by 2a, where a, b, and c are the coefficients of the quadratic equation. In order to simplify the math, we can go ahead and divide through by -3. If we do that, this becomes t squared, this becomes -4t, and this becomes -1 equal to 0. And so using the quadratic formula, the coefficient in front of the t squared is 1. That's our a, this is our b, and this is our c. So substituting in, negative b is -4 plus minus b squared minus 4 times a times c divided by 2 times a. And so out here we have a negative and a negative, that becomes positive. So 4 divided by 2 is 2 plus or minus. We have 4 squared, or -4 squared, which is 16. Negative subtracting a -4 becomes the same as adding 4. It's the square root of 20. Still divided by 2. And so 20 is 4 times 5. So we can bring out take the square root of the 4, which will be 2, and it'll cancel that 2. So this is 2 plus or minus the square root of 5. We have two solutions here. Since we're dealing with the time period between 0 seconds and 10 seconds, we only want the positive solution. And so the positive solution, will be 2 plus the square root of 5. If we punch that into our calculators, that's approximately 4.236 seconds. So that is the time at which we turn around. If we want to find the position corresponding to that time, then we can just substitute that into the previous expression for s that we had. And so just as a reminder, we had found that s is minus 58 plus 3t plus 6t squared minus t cubed, all in units of meters. And so, in essence, we take this time, plug it in to our expression for position, and we get that the position at that time is negative 13.64 at the turn. And so, in order to determine the total distance traveled, we need to determine the displacement going forward plus the displacement going backwards. So the total distance is the displacement from 0 seconds to 4.236 seconds, or the absolute value of the displacement, because we don't care if we're going forward or backwards, we just care about the magnitude, plus the displacement after the turn, so from 4.23 seconds to 10 seconds. And so the displacement going forward, we ended up at minus 13.64. We subtract where we started, which was negative 58. Then we have our distance going backwards. We end up at minus 428. We subtract where we started, which was negative 13.64. We add those two numbers together. That works out to be approximately 458.7 meters. That's the total distance traveled. And so this concludes this example, example 2.2-2.